so now we're going to go more in detail about the acceleration vector. Okay, so acceleration vector. All right, so I'll draw a little diagram here. Let's say we have some curve, okay, and that was a really bad curve, so I'm just going to try that again. Okay, that was better. All right, so let's say we have some particle, okay, and it's moving, I don't know, let's say it's accelerating this way, okay, so it's kind of moving down and to the right, okay, so here's our acceleration vector, so that's A. Okay, so now we have, what we're going to do is actually break this acceleration vector down into like components, okay? So what we're going to have is use our tangent vector, our unit tangent. So let's say here's our unit tangent. So this is pointing tangent to the motion, or tangent to the curve, right? So this is our unit tangent vector. And I'll denote this, usually I do an arrow, like a normal arrow, but here I'll put a little hat on it, because that means unit, right? That just specifically means unit vector. So t hat is our unit tangent vector, and that is given by r prime of t over the magnitude of that vector, r prime of t. Okay, and so this is one of the directions that we'll be measuring our acceleration vector in, and the other direction is in the normal direction. So again, normal means pointing inward into the way the curve is bending toward, okay, at that point. So this is our unit normal, so I'll put a little hat over that one too. So n is our unit normal, and this is equal to the, actually I'll put the little hat there, okay, the derivative of the unit tangent vector over the magnitude of that derivative of the unit tangent vector. Okay, so we have these two directions basically. So we have going parallel with the tangent vector and then in the normal direction. So the tangential direction and the normal direction. Okay, so what we're going to do is what it's called is decomposing our, so we're going to decompose our acceleration vector, our a of t, into the following. So what we want to do is get something that looks like this. A of t is equal to an a, some coefficient. Okay, so this stands for a coefficient. It's not going to have an arrow over the a here. But then times the unit tangent vector plus another coefficient, this time this belongs with the normal one, times the unit normal vector. Okay, so this is the tangential coefficient. So I'll just put tan coefficient. This is the unit tangent vector, so unit tangent. Okay, this is the normal coefficient. That's what it's called, normal coefficient. And the last thing that we see here is just our unit normal. Okay, so unit normal. Okay, so this is what we're striving towards to find. And pictorially, continuing my picture here, making it a little bit more detailed. So what we want to do is take this acceleration vector, the one pointing down and to the right diagonally, right? And what we want to do is kind of project it. Basically, that's what we're going to be doing, is projecting it onto the tangential direction. So how much does it point in this direction? So this entire vector here, the long one, that's actually going to be a sub t hat times t hat. Okay, so that's going to compose our first term here. That's what this long one means. And then we're going to project our acceleration vector onto the normal line, into the normal direction. So that one's going to be a vector like looking like this. It's that long, okay? And this one, this entire thing is going to be the second term. That's what it's going to be composed of. So it'll be a sub n, so that's our coefficient, our normal coefficient, times the unit normal. Okay, so as you can see, then if you add this vector here, added with this vector here, what you get in a vector addition version of calculating things is you get the original acceleration vector back, the one pointing down and to the right, that is diagonal. Okay, so what we're going to do now is kind of break everything down in that formula that I just showed you, the decomposition of the acceleration vector. We're going to break that down in more of a calculus, or not calculus, but like a calculated technical way. So first of all, we're going to define the unit tangent vector as the r prime of t over magnitude of r prime of t. Okay, and this is also equal to v the velocity vector over the speed. Yeah, just speed. Also known as velocity vector over the magnitude of the velocity vector, which is speed. Okay, so there are a bunch of different ways to write it. And the important one here, so we're going to take this left side and the right side that we arrived at, and I'm going to kind of rearrange it to say that v of t, our velocity vector, is equal to the unit tangent vector times the magnitude of the velocity vector, which another way to write that is the unit tangent times speed. Okay? So this one equation here, now we'll take the left and the right side. What I'm going to do now is actually differentiate both sides. So we're going to ddt both sides. ddt. Okay? So on the left side, all we get is the acceleration vector. And then on the right side, though, we do have a product rule going on here. Not a dot one or a cross product, but just a normal like multiplication, right? So what we're going to have is t, the tangent vector, times v prime of t. And then we have plus, and we'll keep this one the same and take the derivative of the unit tangent. Okay, so now that we have this, what we want to do is actually kind of mirror the decomposition of the acceleration vector. So we want this term here to be some a sub t hat, and then times that t hat. That's what we want this one to match up with. And then we want this one to match up with an a sub n hat times n hat. Okay, so for the first term, we already see that there's a t hat and a t hat, right? So those ones are the same. So that means that a sub t hat has to equal the other thing there, right? So these ones match and those ones match. So then we have that t hat is the same as t hat, okay? And then that, so t hat equals t hat, and a sub t hat is equal to v, the first derivative of the speed, okay? So we solved for the coefficient there. And now let's figure out what's going on the right, on the second term here. So another way to rewrite the t prime, the t hat prime of t, is this way. So we could rewrite this line here as v of t times, what else? And we can rewrite that as vt times curvature of t times the normal with respect to t, or of t. Okay? So that one actually comes from a derivation of the formula for the unit normal vector. I'll explain this part more in detail on the next slide.